about learning some Gaussian graphical models. So first, what's a Gaussian graphical model? Well, it's really just a Gaussian distribution. Like, oh, it's gone. Should I do something? Okay, it's back. It's just a Gaussian distribution. And so what's a Gaussian distribution? Well, I could just say that it's something where the density looks like e to a quadratic form. So it looks like e to the x transpose sigma inverse x over 2. And here sigma, right, is the covariance matrix. And because it's sigma inverse, which shows up in the exponent, we let theta equal sigma inverse, and we call this the precision matrix. And so what makes this a graphical model in the same sense that we know like Ising models are graphical models? Well, first we have to define the graph. So the graph, it's the vertices are the coordinates 1 through n of our random vector. And you have an edge between nodes I and node j if the corresponding entry of the precision matrix, so the inverse covariance, is not 0. And the reason this is a graphical model is it has this key thing called a Markov property. And so, let's see if my laser pointer works. So to illustrate the Markov property, if you look at this graph, I have nodes x1, x4, they're connected via x2. And the idea is that the edges in the graph correspond to direct interactions. And what this means is that because x1 and x4 sort of only interact through x2, if I were to condition on x2 and look at the residuals of x1 and x4, those now become independent. So that's exactly the same as the Markov property in the Ising model. Yeah. So why do we care about Gaussian graphical models? So when we say Gaussian graphical model, it more or less means we are studying Gaussian distributions where this theta matrix, the precision matrix, is sparse. And one reason this is good is just the obvious interpretability reason. Like I can meaningfully say that some things are not related once I condition out on other things. And then another reason, which is sort of very important in practice, is that such a model could be learnable from fewer samples than a general Gaussian distribution is. So if I want to learn the covariance matrix from data, we know from lower bounds for PCA that you need like the dimension number of samples. But because I've assumed sparsity, it's often possible to learn from fewer samples. So Gaussian graphical models also, they're pretty popular throughout sort of a wide array of disciplines for both modeling and sort of exploratory data analysis. One example that comes up is that sort of in biology, people study these interactions between genes. I'm not an expert in biology, but I think basically you can have the situation where one gene inhibits another gene from expressing itself, and also even more complicated interactions. And even though those are very complicated, we would like to learn something about them, and sort of tools like Gaussian graphical models are very popular for trying to solve this problem. Yeah, so I have an example from the scientific literature. This is a paper from 2019 by Zhao and Duan. It's called Cancer Genetic Network Inference Using Gaussian Graphical Models. And what they did is like they looked at a bunch of RNA-seq data, and some of it comes from, I think, people with cancer and some from people without cancer. And they sort of, they build Gaussian graphical models based on the people with cancer, and they try to find what are the common edges between all these people. And then they found that this graph is like sort of shared between these models. And if you read the paper, apparently this is like consistent with what some things that are known in the literature about like something called the PI3K pathway. But I didn't understand that part. But what you can see is that people do indeed use this in other fields. Okay. And so now let's sort of mathematically formulate the problem. So we're going to talk about structure learning. And that means I get to get independent samples from the Gaussian graphical model. And my goal is to recover the support of theta, which is the edges of the graph. And so you might ask, why do we study structure learning? Because we could also ask, since theta is a matrix, why don't we ask to recover theta accurately in some distance? But the point is actually those tasks are basically the same, because if I know the support of the theta, then it's actually very easy to fit the entries. So you can just use ordinary least squares in some relatively simple way. So for that reason, we'll focus on recovering the support. And the idea is sort of that you want to succeed instead of using, or n is the dimension, instead of using like n samples, you would like to succeed with only like log n samples. And this is under the assumption that theta is sparse. Okay, so here I put up, I think, what are maybe the 3 most popular algorithms for learning Gaussian graphical models. But there's many others, so it's not an exhaustive list. So one, which is very natural, especially if you know about learning Ising models, is this thing that's called the Meinhausen-Bullmann estimator. And what the idea here is I'm going to look at each node xi, and I'm going to try to learn its neighborhood. So what I do is I set up the lasso, which is just this L1 penalized least squares regression. And I try to predict the node xi from all of the other nodes. And the L1 penalty is supposed to encourage sparsity. And the point is that the optimal predictor is actually sparse. So we would hope that maybe this program will return the W, which is optimal, like for an infinite number of samples. And that would actually tell you exactly the support. So basically, you run this program, you look at W and see where it has non-zero entries, and that's your neighborhood. And then you do that for all nodes, and then you do some procedure like union or intersection to merge them all, and you get the graph. So I think the most popular method in practice is this thing called a graphical lasso. So like Mark mentioned yesterday, that in Ising models, we cannot compute the normalizing constant, which means we can't use methods based off maximum likelihood. But for Gaussian graphical models, we know it's just some kind of determinant. And so you can actually formulate the maximum likelihood program. And that doesn't really make sense to run that normally if you have fewer samples in the dimension. But what you can do is you can add a L1 penalty again. Here we go. And that L1 norm, by writing that, I mean it's the sum of the vector. So it's like literally the L1 penalty on all of the entries of theta. And sometimes people remove the diagonal, but I don't, yeah, otherwise it's the same. Yeah, so that's a very popular algorithm. And a algorithm that was introduced a little more recently and also, I mean, seems to be based off a pretty reasonable idea is this one called climb. So climb is it's an estimator that can be implemented as a linear program. And the idea is, once again, you're going to try to minimize the L1 norm of theta, which is supposed to encourage sparsity. And we know that theta is supposed to be the inverse to sigma. So they literally just encode that as a constraint. So theta sigma minus identity is bounded, and they ask for that to be bounded in infinity norm by some parameter lambda. And so basically, I mean, all 3 of these methods are based on L1, but they all do slightly different things. And you can see that they actually do behave differently in practice. Okay, so there has also been a lot of work on sort of the sample complexity guarantees for learning Gaussian graphical models. And so I'm not going to try to survey every result. But if you start to read these papers, you'll realize that there's a very common assumption, here we go, which is, looks pretty reasonable at first sight, which says that when I look at my precision matrix theta, then I know that that is supposed to be sparse. And so what I would hope is maybe that the L1 norm of the rows of theta is also not too big. And this, again, is the intuition L1 norm is like sparsity. So if you have this assumption that the max L1 norm of the rows of theta grows like a constant as n goes to infinity, then, for example, the climb estimator, it's proven that it can recover theta accurately from log n samples. And this is actually probably one of the weaker guarantees in the literature. Sorry, it's one of the better guarantees because it has weak assumptions. So there's, in order to analyze like the graphical lasso, people have had to make additional assumptions, which include things like incoherence on something called the Fisher information matrix, which It's basically a stronger assumption that ideally you wouldn't have to make. Okay? But let's go back to this assumption, which looks relatively benign. And let's think about what it really means. Well, it's the maximum of the L1 norm. But by Holder's inequality, that's the same as saying if I give mu a vector x, which is bounded in an infinity norm, how big can I make the infinity norm of theta times x? And then if you think about that, that's like the operator norm from L infinity to L infinity, and theta is sigma inverse. So this is just the L infinity to L infinity norm of sigma inverse. And the thing about that is if we look at that, now we're like, oh, that actually looks kind of like a condition number. And pretty much it means that m is small when sigma is well conditioned with respect to this norm. And once you start to think about this, you'll realize that this is actually a little more than a sparsity assumption. So actually, in many models, m actually grows with n as I take n to infinity. So for example, there's a model of a Gaussian process on a 2D lattice called a 2D discrete Gaussian free field. And in this case, you can just compute that m grows like log n. So already you are paying log squared n samples. And then, as I'm going to show on the next slide, if you look at a model that looks kind of like a non-stationary time series, then actually m would grow polynomially in n. And sort of maybe there's an intuition that if you want to have interesting large-scale behavior, you probably want m to be big omega of 1. And so to really illustrate this, it's probably better to look at a picture. So here's a random walk, and it's run for 1,000 time steps. And what we need to think about is what is happening at time 1,000. And the key thing is that at time 1,000, why does the random walk have a lot of variance? And it's not because the last step of the random walk was very big. That has almost no effect on x1000. But it's actually because of its interaction with all of its neighbors that the previous 999 steps made it have a lot of variance. And so if we do this rescaling where we set the variance of x1000 to be 1, which is sort of like you pretty much always want to do some rescaling like this if you're going to use lasso, then when you look at the corresponding entry of the precision matrix, which is 1 over the diagonal entry, that actually is equal to the conditional variance, which is equal to 1 over 1,000, because we scaled by the square root of that. And so you see that in this example, even though the random walk corresponds to a path graph, so the sparsity is 2, this number m is actually on the order of 1,000, so it grows with n. Okay? So one natural thing to wonder is like, well, maybe it's basically the case that we have these guarantees, and it's because m is actually sort of information theoretically a required quantity to control. I mean, because there is some intuition that condition numbers are related to learnability. But fortunately, there's this recent work by Misra, Bouffret, and Lokov, who are, I think, all here, which shows that it's actually not the case. And so this is their theorem. So all they need is a non-degeneracy parameter, which is called kappa. And they require basically that when you look at the ij entry of the precision matrix and you properly normalize it, so this is a proper normalization because if I rescale the coordinates, this doesn't change. So if I have that basically the non-zero entries are not too close to 0 in the proper normalization, then they can guarantee that from d log n over kappa squared samples, you can successfully learn the structure of the graph. And so the point is that doesn't have any dependence on any parameter except d and kappa. And so, for example, how does this differ from a condition number assumption? Is I could, for example, have 2 variables that are almost equal, and that would sort of blow up my condition number, but doesn't change the fact that the model is learnable. And this is close to matching the information theoretic lower bound, which is big omega of log n over kappa squared. And so sort of the remaining question after their work is, can we compete with this guarantee, but using algorithms that run in a time that's not exponential in d? And that's what I'd like to talk about today. So we have 2 basically families of results. One is for a slightly easier model called attractive models. And the next one is on the next slide. So the attractive models, there's actually many terms for this. So sometimes they're called ferromagnetic. I think in Caroline's paper, it's called total positivity because there's some connections to some more general phenomena. But regardless, the assumption is that the off-diagonal entries of theta are not positive. And the reason this makes, the reason we call this attractive is under that assumption, the covariances are all non-negative. And so these models, they actually appear in a surprising variety of places. So there's this paper by Zhu, Garamani, and Lafferty, which was in 2003 in ICML and actually won the 10-year Test of Time Award in 2013. And they actually have some interesting thing where they use basically what would be called a discrete Gaussian free field, which is a special case of this. And they show how it could be useful for semi-supervised learning. Okay. So anyway, if you have that assumption, then we can prove now that there's a simple algorithm which is basically based on a greedy idea, kind of like some of the works on Ising models. And it learns from d log n over kappa squared samples with runtime that's like n squared. And so this matches the guarantee that we previously only had for the n to the d time algorithm. So just for sort of a note, you might wonder, okay, is that the optimal sample complexity? Unfortunately, it's actually not. So in our paper, we also show that the sample complexity is exactly up to constant log n over kappa squared. So this shaves the d factor from the guarantee for the efficient algorithm. And this is again based off some kind of L0 constrained least squares. So that algorithm requires n to the d time to run. But yeah, that's exactly the minimax rate. Okay. So the thing about the previous slide is, okay, that only works for attractive models. Then if I look at my data and I see that there are two variables which have negative covariance, I can just reject. It's not possible that that comes from an attractive model. And so we would like results that apply in that case as well. So unfortunately, we cannot handle the general case, but we can handle a large class of models which are called the Walk-summable models. And yeah, basically, there's many other classes of Gaussian graphical models which people have named, such as the attractive models, and also models where theta is symmetric diagonally dominant. And those models are all contained in this class of Walk-summable models. The definition of Walk-summable, there's many equivalent definitions, but one is that if I look at my matrix and I make all of the off-diagonals to have negative signs, then the matrix remains positive semi-definite. And so maybe one way to think about this is it means that the matrix is sort of robustly positive semi-definite, or maybe it's positive semi-definite for a simple reason. But regardless, under this assumption, we can learn all Walk-summable models with a sample complexity that looks like d log n over kappa to the 4. And so that differs from the L0 constrained guarantees, which can get d log n over kappa squared by this factor of kappa squared.
Stronger than diagonally dominant?
Yeah, so this includes symmetric diagonally dominant. Yeah. So it's a weaker assumption, I guess. Yeah. If the graph is a tree, it's Walk-summable. Definitely if it's an attractive tree. If it's not, then I think you can just flip the signs to make it attractive. So I think it's true that it holds for trees. Yeah. Okay. Yeah. Okay, good.
So here you're doing support recovery, right?
Yes.
So what is the dependence on the minimum strength here?
So kappa is that, that's the condition for, that's basically the assumption for the minimum strength, and it's 1 over kappa to the 4. Yeah. Yeah. The next slide, I'll talk about sort of a more general regression result, so it'll be maybe easier to interpret how it compares to other methods. Okay, but anyway, so this is using this algorithm which we call hybrid MB, which I'll reveal what that is later. But actually, under the same assumption, you can also prove that a simple greedy method also works. And it has the same log n sample complexity, but for various reasons, has a slightly worse dependence on d and kappa. And also, just so it's clear that our algorithms, it's not like we made up a totally different assumption and our algorithms only work under this one, but not the previous one. If you make this assumption that the L1 norms are bounded, you could also prove good guarantees for both of these methods. And the best previous result here is by Anand Kumar, Tan, Huang, and Wilsky. And their algorithm again, had runtime n to the d. Okay? So maybe just to get things started with the analysis, our algorithms use this very common idea in graphical models, which is I have an unsupervised learning problem, but I'm going to change it around and turn it into supervised. So what you do is you look at a node I, and you try to predict it from all the other nodes, just like in the Meinhausen-Bullman estimator. And so that gives you a sparse linear regression problem. And our guarantee for learning walk-summable models is basically given from this following more general result, which lets you do sparse linear regression in a walk-summable model without depending on any norm type quantities. And so the exact guarantee is that if I look at a node I and I try to get the best predictor of node xi, then even without making any non-degeneracy assumption, like I don't have any kappa dependence, I can get a good predictor for xi. And how good is it? Well, compared to the best predictor, which is the conditional expectation, it pays only this factor, or this additive error of sigma squared square root d log n over m. And to compare that, if you do like a n to the d time algorithm, then you can get a better guarantee, which basically removes the square root. But otherwise, it's close to optimal. And so sort of, if you want to interpret this, the sort of important thing is that for the structure recovery task, you really need to get error on the order of sigma squared. And if you use some other, maybe more standard methods, maybe you could only get error on the order of sigma from a small number of samples. And that would totally lose the ability to perform structure recovery. Okay. Okay, so yeah, go ahead. Yeah, W is the thing that's returned by our sparse regression algorithm. So it is node dependent, yeah. Yeah, so basically W is our estimate for the edges coming into node I, yeah. Okay. Good.
Is it a fast rate or is it a slow rate? I'm confused.
Oh, wait. Yeah, it's got a bit of both, right? So it's got the sigma square, which is like the fast rate, but it's got the square root, which technically makes it a slow rate. So it's it would be ideal to just get rid of the square root, and then we could say it's optimal. But who knows if that's possible? Yeah. Okay. So first, I'd like to talk about learning attractive models, because if we study this problem, we actually get a hint about how to solve walk-summable models. Okay. And so the key quantity that we're going to look at here is the conditional variance, which is, well, I defined it there. So it's going to be parameterized by a set S of nodes. And the conditional variance of xi given xs is just how well can I predict xi given the nodes in xs. So I look at the conditional expectation of xi given xs, which is the optimal predictor. And I ask how much remaining variance is there in xi when I use that as my predictor. And the key property is that if you drive this conditional variance down to its minimum, which is, so 1 over theta I, remember, is that's always equal to the conditional variance given everyone besides I. So that's the minimum that this function can achieve. And so if you get a superset of the nodes, the superset of the neighborhood of node I, then variance of xi given xs is just equal to 1 over theta I. And so otherwise, what we can do is we can just compute how big of a gap is there. And no need to follow the details, but basically you just write out what it is, and you use this thing called law of total variance. And after computing that, you'll see that this gap is always lower bounded by kappa squared over theta I. So that means if I can get the gap between this number and this number to be less than kappa squared over theta I, then the gap actually has to be 0, which means I successfully recovered. Okay? And actually, it turns out in the analysis that it's important that you can actually get a somewhat stronger fact, which is you can multiply the right-hand side by how many nodes you are missing. And it turns out this is useful if you really want to optimize the sample complexity. But this first guarantee is important because it's just true in every model. It doesn't require any assumptions. Okay. Yeah. Okay. And so we want to solve the sparse regression problem with a greedy method. It's not sort of an original idea to solve sparse regression with greedy schemes. That's actually a very popular idea. So In particular, there's this paper by Dawson Kempe, which maybe popularized this. And sort of the best possible thing for analyzing a greedy method is probably to have some kind of submodularity statement. And so the great thing is actually people in the past, a few years ago, have actually proved that the conditional variance is a supermodular function. And so what does it mean supermodular? Well, basically, the idea here is that if I were to add node j to my set S, and I compare to adding node j to a set T that is bigger, then it's less effective. And so the reason this is good for a greedy algorithm is you want to say, basically the key thing to prove is that I can make a lot of progress in the first step. And then all the other steps are sort of the same as the first step, so if I can prove that, I'll prove that a greedy algorithm works. And so here I can take on the left-hand side for the set to be the empty set. And so that's exactly going to be the gap in conditional variance after one step of greedy. And I'll pick j to be a neighbor of node I, and I can get a lower bound on the right-hand side. So this is actually exactly the thing I just showed you. It's like if I don't have all the neighbors, then if I add one more, I get a gain of kappa squared. So yeah. And actually, I guess more generally, like you can get like an exponential rate for a greedy algorithm under this assumption. But anyway, yeah, the conditional variance is supermodular, which basically is going to mean greedy methods are going to work well. And so it's sort of interesting. So there's these two papers which don't reference each other, which both prove this fact. I think they're from different communities. So actually, if you're bored, you can look at our paper, and we actually have a third proof, which is different from both of them. And it's kind of fun. It uses just like, basically you just tailor series expand sigma. But anyway, it's a known fact.
Does it meet the Gaussian assumption? They have an attractive easing. Is that true?
If you have an attractive easing, I'm not aware of this being a known result for attractive easing models. It could be false. I didn't think about it. There are related facts that are true. Yeah. That's a good question. Yeah, all of those proofs are not going to generalize beyond the Gaussian case. Okay, so anyway, we have this supermodularity, so let's start analyzing the greedy algorithm. I mean, this is kind of standard. So for now, we don't want to analyze what happens because of all the sampling noise, because that's a bit complicated. So I just suppose I have an infinite amount of data, and I just want to prove greedy is going to successfully learn a superset of the neighborhood. Okay, so what's my greedy algorithm is at every step, I pick the element j, which is going to decrease my conditional variance as much as possible, and I add that to my set. And I just keep doing that step after step. Okay, and then this is the thing I was trying to say about the exponential rate, is that for this algorithm, as long as my set doesn't contain all the neighbors, by following greedy, I decrease the conditional variance by 1 minus 1 over d. And also, I know that if I get that function, sorry, this should be 1 plus kappa squared over theta I. But anyway, if I get that function down near its minimum, then I've successfully learned the whole neighborhood. And so I just use induction. Okay, if I do this for t steps, I get a multiple shrinkage of 1 minus 1 over d to the t. And I need to get down to an error of kappa squared. And so if I use log theta I variance xi over kappa squared steps, then I successfully learn the neighborhood. Yeah. Okay. But the problem here is actually we're not allowed to depend on log theta I variance xi because that's still a condition number type quantity. So we improved the dependence from polynomial to logarithmic, but it's still forbidden. And so this may seem like a technical problem, but it's actually it's a good idea to understand how to fix this. Okay, so the first idea is show at the 0th step that this variance is actually bounded as a function of the parameters we have. It turns out that's impossible because you can just blow it up independent of all of those. So the correct thing to show is actually that the variance after the first step is bounded. So for this, we need some more tools. So there's this basic fact about walk-summable models. So it's interesting because actually the motivation for introducing walk-summable models was to generalize STD, but actually it wasn't until a few years later that people realized there's a simple connection between them, which is that if you have a STD, if you have a walk-summable graphical model, then there's always a way to rescale the coordinates of the model so that the precision matrix becomes symmetric diagonally dominant. And this is actually, it's quite similar to classical facts in linear algebra, but I couldn't find this exact statement in the literature, but maybe it's somewhere. But anyway, it was definitely proven in this paper by Rosi, Thaler, and Tatikonda. What this means for attractive models, which are a special case of Walk-summable, is that when I rescale, it becomes something called a generalized Laplacian. So that's just what it means to be attractive and STD. We call that a generalized Laplacian. And so the corresponding Gaussian graphical model becomes what would be known as a discrete Gaussian free field. And the thing that's important is now the covariance matrix is the inverse of a Laplacian. And there's all of these beautiful facts about this, which means that you can interpret the entries basically in terms of electrical quantities. So I thought I will review this really quickly because I think I wasn't familiar with this beforehand. So basically, you know from Ohm's law that the current is the voltage divided by the resistance. And the voltage on an edge is the change in the potential. So there's some potential function V, and if you look at Vi minus Vj, that's exactly the voltage on edge ij. So if you sort of think about this, if I want to compute the net current out of a node, then I sort of just need to sum the currents along every edge. And if I write this in terms of matrices, I define this matrix with Lij as negative 1 over Rij. Because, you define that, we call 1 over Rij the conductance of edge ij. And you define Lii to be given by, this should be the sum of 1 over Rij, my bad. And then what you get is that the net current out of node I can be given by multiplying the voltage by the Laplacian and looking at the ith coordinate. And okay, so anyway, what we get from that is the Laplacian is a map that goes from the voltages to the net currents. And so if you invert it, then what you get is a map that goes from currents to voltages. And now if we look at this funny thing, Ei minus Ej transpose inverse Laplacian Ei minus Ej, well, the first part, the Laplacian inverse Ei minus Ej, is like it's the voltage gap between node I and node j when I put in unit current. The Laplacian inverse Ei minus Ej is the vector of all of the voltages. And when I hit it with Ei minus Ej, it computes the voltage gap between nodes I and j. And just by the definition of effective resistance, that's actually the effective resistance. So it's like, okay. So maybe we couldn't follow that live, but the point is it's a relatively simple fact. And if you think about it, you can prove it yourself. And then there's this one more complication. So the matrix above L I defined, it would be called a Laplacian. Technically, in the general SDD case, the diagonal entries can be bigger than they would be in the Laplacian. And we call that a generalized Laplacian. And the point is that it has a very similar electrical interpretation, but it involves basically this idea of electrical ground. So you have some excess on the diagonals, and that corresponds to connecting some resistors to this additional node, which we call ground. Yeah. Okay, but anyway, once we know this fact, then we can actually prove that the conditional variance is bounded after the first step. And the point is that this is not so easy to prove, but once I reinterpret electrically, it's actually easy to prove. So first, I know my attractive model is really just a Laplacian secretly, or the theta is just a Laplacian. And now, when I interpret this electrically, the variance of xi given xj is just like the effective resistance from node I to ground. And when I condition on xj, what that means is I connect node j to the ground node with a wire that has no resistance. So effectively, that's the same as saying that node j becomes the ground node. And so now, what's an upper bound on the variance? If I interpret in terms of resistance, I'm basically asking, what's the effective resistance from node I to node j? And well, we know that there is a direct connection which has resistance 1 over theta ij. And there might be other connections through the graph which are actually going to make this quantity smaller, but we can ignore them and get an upper bound on the variance of 1 over theta ij. And now if we look at this, to get an upper bound, we need to lower bound theta ij. But we use the kappa non-degeneracy, and we use the fact that we've rescaled so the model is SDD. And then just writing that out and doing some algebra, we get an upper bound of 1 over kappa squared theta I as promised. Okay. Okay, and so now we have fixed the analysis. And so you see that if I have d log 1 over kappa squared rounds, then I successfully learn the neighborhood of the true node. And there's this thing which is in all of these algorithms where you find a superset. Once you find a superset, then pruning is actually easy. So this is just the same as in Guy's paper. And so in this case, what you use is actually the same as what in statistics we call a regression t-test. And then here I put some, so all of that was assuming there's infinitely many samples. Like if you don't care about the dependence on d and kappa that much, then just knowing that is going to give you some bound that grows like log n. If you care about d and kappa, then you need to like sort of correctly analyze everything. And then you need to use some sort of classical facts about ordinary least squares, which I thought I won't get into. And sort of interestingly, I said that you could improve this lower bound using this multiplicative term, which is the neighborhood without the set. And it just turns out that's really important for getting a good bound. So that's sort of interesting, but I won't talk about it anymore. So we still have some time left, so let's talk about walk-summable models. What happens in walk-summable models is that, before we love supermodularity for greedy algorithms, but it's just totally not true in this case. So I won't try to belabor the point, but basically you can write down a model on 3 nodes, and what happens is that if I add one of my neighbors, then it doesn't help the conditional variance that much compared to adding 2 of my neighbors. So that means that there's basically no supermodularity. And so what we need is to prove, well, I promised you at the end that greedy and prune does work for this model. So a natural question to ask is, what are some other ways to prove greedy methods work? There are actually, of course, a lot. One that's like particularly relevant is in optimization. There's something called a conditional gradient method, which is actually a greedy method. And the guarantee for that doesn't have anything to do with submodularity. And actually what you need there is you need a norm bound. So you need something like a L1 norm bound on the set you're optimizing over. And so this actually, if you think about this, it's like, oh, actually what we want to do is we actually want to bring back this L1 thing. So if we can get a bound on the L1 norm, we could prove greedy works, and also we could prove other methods work. And so here is the key fact is, based off the attractive models, I know I should always analyze things after 1 step of greedy. I mean, this might actually be kind of related to this pinning idea. Like the field is, there might be a lot of nasty things are super correlated, but if I were to take 1 step of greedy, it sort of cleans things up. So regardless, yeah, I write down what the regression model is after doing 1 step of greedy. So J is the node I picked in the first step. And so the regression model is just this. I just subtracted a bunch of conditional expectations. And then when I want to analyze regression, I should probably rescale my regressors to have unit variance. So I do that. And now suddenly, even though before taking the first step of greedy, the L1 norm was totally unbounded, now there is a bound just in terms of D. And so it turns out that this quantity, the sum of theta ik over theta I, square root variance, is bounded by square root 3D over theta I. So I don't really have time to include the complete proof, but the thing to think about here is like, well, I have a product of these 2 terms, theta ik and the variance. And what happens is like if theta ik is really big, then that means nodes I and k are really well connected. But that means that if I do 1 step of greedy, I could have picked node k, in which case I would have shrunk the variance at node I by a lot. And so that means that the variance at node I should be very small after 1 step of greedy, even if I didn't pick k. And because nodes I and k are well connected, this actually means that the variance of xk given xj should be small as well. So it's this funny thing where either theta ik is small, in which case you don't care, or if theta ik is big, then things might have been really correlated, but 1 step of greedy should have fixed the problem. Unfortunately, it doesn't work for general models, so you really do need to do some electrical thing to make this into a rigorous fact. But it does work out. Okay, so here's basically the algorithm. Is I do 1 step of greedy. Now I set up the same lasso problem that I described before. I mean, for reasons of convenience, I set up as the constrained lasso instead of the penalized lasso. That's not fundamental. And so I solve that, and then I do some relatively straightforward thresholding, and I recover the neighborhood of node I. Okay? So there's a bunch of complications here because I use like a parameter theta I, which I don't know, and also I use some conditional expectation, which I also don't exactly know. So basically, there's a way to fix this, which is just instead of having the conditional expectation, you add an additional coefficient on xj, and you fit that. And then now you need to analyze fitting this model, which if you just want to do it from first principles is not that easy, but fortunately there are some really powerful frameworks people have. And so when you use that, you get some bound that looks like this, and you just plug in everything and you get the stated result for sparse regression. And from that, you get the corresponding result for structure recovery, so everything works out. And to analyze greedy, you go back, and instead of using the ERM, it's pretty straightforward to analyze greedy given an L1 constraint, and that gives you the slightly worse dependence on D and kappa, but it all works out. Okay, so in the last few minutes, here are some simulations we did. So these are basically, there are some models. The left two involve, basically I create a path and I throw in some cliques, and the right model is actually just a path. And what you can see from these graphs is that all of these models that people have proposed in the past, so there's climb, there's A-climb, which is a variant of it, Lasso is the graphical lasso, and MB, which is this lasso-based algorithm. And you can always find an example where they break. So the theory is not, we're not totally off base. Like if you look at large models which have interesting dependency structure, then those algorithms actually, their sample complexity scales faster than log n. I mean, it looks like they all scale linearly in some case. And also we did, grid search over parameters and so on, so I think this is a relatively trustworthy experiment. Okay, we also ran it on some Riboflavin data set. I won't belabor this, it's a relatively small data set. But one thing that's interesting is you see that the parameter m is comparable to the parameter n, which suggests that our concern might actually be valid in real data as well. Okay, so here's my summary is we got efficient algorithms for learning all walk-summable models, which have the correct dependence on n. Sort of a key idea in the analysis, which I didn't maybe emphasize as much as I could have, is it's really important if you want to analyze this to rescale to be SDD, because the different rows of theta are otherwise they have different units, so they're not even comparable, and that's pretty much going to that would be a huge problem for the analysis. So it's really important to do this rescaling. We kind of just set everything to variance 1, but that might not be the optimal thing to do all the time. So that's sort of a takeaway. So there are a ton of open questions. I just put 2 that I think are particularly interesting. So the big, obvious one is to learn all Gaussian graphical models with log n samples. You can break every algorithm that basically is proposed by coming up with some example which has some nasty cancellations. But there's not like a computationally hard example. So maybe you can learn it, you just need the right algorithm. And then like everything that we considered here, we didn't quite get the information theoretic optimal. And I have no idea for which of these the gaps could be eliminated or for which they're unavoidable. And we have no evidence either way. So I think that's like a super interesting question as well. And that's it. Thanks. Yeah.
There was a lot, so I got a bit confused.
Oh, sorry.
Just to clarify in my head, I'm not sure what you use for the analysis and what you use for the algorithm. So at some point you wrote the result. Let's say I just go back to the neighborhood selection result, right?
Yeah.
This Sparse linear regression. You do use greedy search to find the support of these guys, and then once you have it, you do an L1 constraint optimization on this?
Oh, okay, yeah. So this might be confusing because for the attractive models, we just use greedy and ordinary least squares. So there's no L1 involved. For the attractive model, the key point was you do one step of greedy, and then you set up the lasso. So it's not like we find the support. We just do one step of greedy, and that sort of makes somehow that makes the problem better behaved, and then we run lasso, and we can prove this works. Yeah.
So given that algorithm doesn't really assume any structure that we are assuming for the theorem,
Yeah.
what if we sort of use the algorithm that you have for settings which are beyond, let's
Walk-summable. Yeah. That, I mean, another thing we saw here is that the sort of the difference, at least in the level of entries to a walk-summable matrix, is not that big in this example. So one thing you might hope is to prove a guarantee that when the distance to walk-summability is not big, then this algorithm still works. I don't know how to prove that. And also, you can just run it in real life, and that's very interesting as well. Yeah.
Sorry, and if I use L0 penalization, do I get the information theoretic optimal, or?
Oh, there is this weird thing where the upper bound is d log n over kappa squared, and that comes from L0. And the lower bound is log n over kappa squared, so it may be that the lower bound is not tight. So if in that case, it would be true. But as far as I know, that's not known. I think that's a reasonable guess. Yeah. Right. So definitely so maybe there could be a general result for learning all graphical models that are totally positive, but so far I don't know of any such result.